Welcome to my channel. This video give you an information about resonance effect and hyperconjugation. First, we will discuss about resonance effect. It is redistribution of electrons in unsaturated system via pi bonds. Redistribution of electrons in unsaturated system via pi bonds. Most of the times molecule and its properties cannot be explained by single structure, and the properties can be explained by two or more individual structures of that molecule which are interconvertible, and those individual structures are called as resonance structures or canonical structures. So those resonance or canonical structures can explain the properties of molecule very well. So far, those canonical or resonance structures are not real. Those canonical or resonance structures are not real. They are hypothetical. Those canonical or resonance structures are hypothetical. But the actual structure of the molecule is hybrid structure. As like in benzene, we know the benzene, this is written like this, as there are carbon carbon single bonds, carbon carbon double bonds, but as per our observation of this molecule, we supposed to say that the carbon carbon bond length or carbon carbon double bond length should be like this, 1.54 angstrom and 1.34 angstrom, but actually it is observed at 1.39 angstrom. It is on the basis of X-ray crystallographic study. It was observed that the bond length is 1.39 angstrom, and it is written like this as a hybrid structure. This is a hybrid structure which explains the properties of that particular molecule. So this one example we have taken here, benzene. The hybrid structure of benzene is like this, is based on this particular bond length. It is not actually carbon carbon single bond or carbon carbon double bond, and it is 1.39 angstrom. It is because of the having not either carbon carbon single bond nature or carbon carbon double bond nature. It is in between that, because of, and this is because of redistribution of those electrons present in the pi bond in this particular benzene molecule, and it is written as hybrid structure which explain the properties of that molecule. The necessary conditions for resonance First necessary condition is when we are writing the canonical structure, those canonical structures written by putting double-headed arrow, that is between two structures, between two structures. Suppose we have butadiene. When you are writing the resonance in butadiene, you have to write this double-headed arrow in between. You can have negative charge here, positive charge. Second important thing, or second important necessary condition for resonance, it is very important that all atoms must be in one plane. All atoms those are taking part in resonance must be in one plane. Third one, during writing resonance, only the movement of electron, only the movement of electrons and the position of atoms remain as such, or atoms are not going to shifted from one place to another place. So only there is a movement of electrons. All canonical forms must be bona fide. That means carbon must have four bonds, nitrogen must have three bonds, and oxygen with two bonds. So when you are writing resonating structures, your carbon should have four bonds, nitrogen three bonds, and oxygen two bonds. When you are writing less than that or more than that, that time you need to put some charges on them. For example, if you have CH3OH, when we are writing like this, we will have CH3OH, here we have double bond and the positive charge. Now the carbon have five bonds and oxygen having three bonds. So this is not the correct way of writing the canonical forms. Fifth one, resonance hybrid is more stable than other resonating structures. Resonance hybrid is more stable than other resonating structures. For example, In benzene, we can have delocalization of those carbon-carbon double bonds in this fashion, and you'll have another resonating structure. There is shifting of carbon-carbon double bonds. So you'll have those two canonical forms, and you can write resonance hybrid for this. This is a resonance hybrid. It is more stable than that of a structure 1 and 2. When you are writing resonating structures and the structure getting a negative charge on electronegative atom, negative charge on electronegative atom, that structure is more stable. Structure getting negative charge on electronegative atom, that structure is more stable. For example, if you have acetaldehyde converted into anion, here in this structure we have negative charge on carbon. If it is get resonated over the C double bond O, you can write another canonical structure in which you are getting a negative charge on oxygen. This is more stable than this one. Here we have negative charge on carbon, and in this structure you have negative charge on oxygen. So the negative charge on oxygen is more electronegative than carbon, so this is more stable structure. In this case, as we have seen earlier, it is going to be resonated like this. You will have generation of double bond at this position. This will get positively charged, this will get negatively charged. So this is structure number 1, this is structure number 2. And suppose we can write one more structure by such type of delocalization. So you will get double bond here. Now here will be the positive charge, and here will be the negative charge. As we said, we can write resonance hybrid for this also. So you'll have this resonance hybrid, and if you look at the structure 1 and 2 and 3, so structure 1 having two carbon-carbon double bonds, structure 2 in which you have at both ends you have charges negative and positive. Structure 3 is having charges very close to each other. So structure 1 and structure 2 is going to have more contribution for resonance hybrid. This is your resonance hybrid having partial double bonds between, suppose we number the carbons 1, 2, 3 and 4. We have as such in your structure number 1 there is a double bond in between carbon number 1, 2 and 3, 4. In carbon number in your structure number 2 there is a carbon-carbon double bond in between carbon number 2 and 3. So structure 1 and 2 having, or your structure number 2 having more charge separation, so it contributes more for resonance hybrid. And the energy of actual molecule is lower than energy of the resonance form. Hence, resonance hybrid is more stable than the resonance forms, and therefore resonance hybrid is the more stable than other resonating structure. Resonance effect is classified into two groups. Number one is electron donating resonance effect, denoted by plus R. The atoms or groups which can donate the electrons by resonance are called as electron donating groups. Here we have a list of some groups like O minus, C double bond O, O minus, F, Cl, Br, I, Nr2, OH, SH, Sr are some groups which are going to show plus R effect. Second class of resonance effect is electron withdrawing resonance effect, which is denoted by minus R. The atoms or groups which are going to withdraw electrons by resonance fashion are said to be having minus R effect. Here we have some examples of that. Nitro group, SO2R, carbonyls, like aldehyde ketone, then nitriles are some groups which are going to show minus R effect. With this, we are going to have some more uh, information about writing the resonating structures for different organic molecules. First, we will take one example of CO2, carbon dioxide. We can write the structure of carbon dioxide. This is the structure of carbon dioxide. We can have delocalization of the pi electrons in this fashion. This is the resonance arrow you have to write in between, and then you'll get the formation of negative charge on this oxygen as the electrons are going on the oxygen, and C double bond O, and this carbon become positively charged. Now again we have delocalization of the negative charge towards the next C double bond O, so you'll have generation of C double bond O and O minus. Again this carbon become positively charged. So here this is the first original structure of your carbon dioxide. By delocalization of those pi electrons over the oxygen, we get negative charge here, and positive charge on the carbon. This is the second structure, and this one is the third structure. So second and third structure are identical, and we can write resonance hybrid for this. Here on both the oxygen we are getting negative charge, so therefore we write delta negative charge on the oxygen, and the carbon getting positively charged, so therefore we write delta positive charge on carbon. This way you can write the resonating structures of carbon dioxide. Second example, we take carbonate CO3 2 minus. So we can write like this: O minus, O minus. This is the carbonate. We have oxygen with the negative charges, so this will give electrons to form C double bond O, and we'll have opening of this carbon oxygen double bond. So you'll write the resonance arrow in between, and you will have now this oxygen get negative charge, carbon oxygen double bond formation, and this oxygen will have negative charge. Now again this negative charge come into picture, and that give you the formation of this new CO bond, and again opening of this C double bond O. We'll get the next picture, that is having a negative charge on oxygen, carbon oxygen double bond formation, and this oxygen become negatively charged. Now we can write resonance hybrid for this: oxygen, carbon, oxygen, and oxygen. In all the cases we have formation of C double bond O, C double bond O, C double bond O, all having generation of double bond character, and all the oxygens are getting negatively charged, so all oxygen will acquire delta negative charge. This is the resonance hybrid, and as such your molecule is having two negative charges, so we can write the resonance hybrid like this, having two negative charge on whole structure. Instead of writing partial negative charges, we can directly write two negative charges on the whole molecule. So those are two examples we have taken, which are primitive examples, or some demonstrative examples how to write the resonance structures, how you can delocalize the electrons. Here we are writing the structures having a negative charge on more electronegative atom and positive charge on less electronegative atom. Here positive charge on carbon, negative charge on oxygen. Accordingly we have shifting of pi electrons. Now as we have already discussed, there are two type of groups responsible for electron donation as well as electron withdrawing. So accordingly we will see how they are going to show plus R as well as minus R effect. So let's take some examples like that, having some groups or atoms attached to the aromatic system which are responsible for electron donation as well as electron withdrawing. First we will take an example of phenol. In your phenol, benzene ring is having attachment with the OH group. So when you try to write the resonance structures of phenol, oxygen is having two unshared pairs of electrons. Those two unshared pairs of electrons are used by oxygen to donate. So here that oxygen lone pair get delocalized over the C double bond C of the benzene ring, and thereby we get the formation of new structure having negative charge on the carbon of the benzene ring. We get the formation of C double bond O here with the positive charge on the oxygen. Now this negative charge get delocalized over the next carbon-carbon double bond. You'll get another structure having negative charge at this position. You get double bond at this position and C double bond OH with the positive charge. Now again this negative charge delocalize to next carbon-carbon double bond. You get this one here. Now this carbon-carbon double bond is formed over here and we get negative charge here, and at last this negative charge is going to neutralize the positive charge of oxygen, and we can write the resonance hybrid for this OH. Here in your molecule we are getting generation of negative charge on the carbon at this carbon, this carbon and this carbon. So we write partial negative charge at that carbon and oxygen getting positively charged, therefore it requires delta positive charge. So this is a resonance hybrid for phenol. Likewise, we take one more example of electron withdrawing group like benzaldehyde. In case of benzaldehyde, we have benzene ring attached to the C double bond H, that is carbonyl group. So we can write resonance structures for benzaldehyde also. In this case, we have the C double bond O attached to the carbon-carbon double bonds. Therefore, we have shifting of electrons in this fashion, and you get the structure like this. We get this carbon-carbon double bond formation here, and carbon-oxygen single bond with a negative charge, and this carbon now become positively charged. Rest of the double bonds remains as such. Now again this carbon-carbon double bond is neutralizing the positive charge here, and we get the formation of positive charge at this carbon. This is the new carbon-carbon bond formed. Then your C double bond C, then O minus and hydrogen. Again this carbon-carbon double bond neutralizes the positive charge of this carbon. You'll get the generation of positive charge at this position. Those double bonds will be there, then O minus and H. Now at last your negatively charged oxygen is going to neutralize the positive charge of this carbon, and you will get the structure and we can write resonance hybrid for this. Oxygen, again we write dotted line, and here oxygen getting negatively charged, so we write delta negative charge on the oxygen, and those carbons getting positively charged, so we write delta positive charge at this carbon and this carbon. So those are the resonance structures we have written, and this is the resonance hybrid for your benzaldehyde. So here in case of phenol, that OH group is going to donate the electron to the benzene ring, and we are getting negative charge on the benzene ring, and therefore this OH group shows plus R effect, and here this group is going to show minus R effect, as it is going to generate the positive charge on the benzene ring. That means the ring become electron deficient, and therefore it shows minus R effect. So that's what about the resonance effect. It is delocalization of or redistribution of electrons over the pi system. There are two type of resonance effects, plus R and minus R. Plus R, which is going to increase the electron density, and minus R will going to decrease the electron density. Second part of our lecture is hyperconjugation. So the hyperconjugation is modification of resonance effect. It is a modification of resonance effect. Because of this hyperconjugation, there is a change in physical properties of the molecule. Also, in case of hyperconjugation, there is a delocalization of electrons, but there is a delocalization of sigma electrons. Delocalization of sigma electrons. Delocalization of sigma electrons. This delocalization of sigma electrons is over the pi system. Over the pi system. So we have already seen at the time of inductive effect, when you have alkyl group attached to any heteroatom or any other substrate. For example, you can have CH3. If it is attached to any other atom, it shows plus I effect, that already we have discussed at the time of inductive effect. When you put some other alkyl substituent like CH3, CH2, or we can have isopropyl group, all are able to show plus I effect. If you have tertiary butyl group, it is also going to show, all are going to show plus I effect, but this is going to have strong plus I, and here we have weak plus I, or effect is weak and here effect is strong. So this is good electron donor. Tertiary butyl group is having strong plus I effect as compared to methyl group. But when these groups, suppose it is there bonded to the saturated system, if it is there, but when it is bonded to the unsaturated system or to the benzene ring, suppose we put the methyl group on benzene and tertiary butyl group on benzene. CH3, CH3 and CH3. So when you have methyl and tertiary butyl group on your benzene, the order of electron donation is exactly opposite. Here, this methyl group is good electron donor when it is attached to the aromatic ring, and tertiary butyl group is not that much good electron donor when it is attached to the aromatic ring. So this change in behavior is because of hyperconjugation, or this change in behavior can be explained with the help of hyperconjugation. So the delocalization of sigma electrons is possible in case of this methyl group attached to the benzene ring, that is in case of toluene, and such type of delocalization of sigma electron is not possible in case of tertiary butyl benzene. So that we can understood with the help of this particular delocalization, we can write this toluene in this form: C H H and H. So here this is suppose it is an alpha carbon with respect to benzene ring, or with respect to carbon of the benzene ring, and this is the CH bond going to be broken, and the sigma electrons from this CH bond get shifted towards the carbon carbon double bond formation, and you'll get the negative charge at this carbon. You'll have structure after delocalization of sigma electron, that is the negative charge at this carbon will get the double bond here and CH2 with the loss of this hydrogen as H plus. It is going to be in the form of H plus, and then we can have those remaining carbon carbon double bond. As such, it will going to be resonated as like earlier in case of resonance effect. Same way we have delocalization of this negative charge to the next carbon carbon double bond. We get the negative charge here, this double bond as such, and your CH2. Now again this is going to be resonated over the next carbon carbon double bond, and we get this one, double bond. Here is the negative charge, CH2. So here this hyperconjugation effect of the methyl group makes the aromatic ring electron rich, and therefore this group is going to show which effect we say plus R effect, or hyperconjugation is going to show electron donating resonance effect. So this hydrogen which is going to be removed from this carbon hydrogen bond cleavage, this hydrogen is not going to be free. It is there in the vicinity of carbon. Which carbon? This CH2 carbon. And those are the different structures we can write. Those are some hyperconjugative structures. We can say those are the hyperconjugative structures. Okay, as already we have discussed, when you are going from methyl to tertiary butyl, or we have compared methyl and tertiary butyl. In case of methyl we have uh, electron donation, but in case of tertiary butyl there is no electron donation by hyperconjugation, and this is why, because of decrease in number of this alpha carbon hydrogen bond. This alpha carbon hydrogen bond is very important as far the hyperconjugation is concerned. So when you have this CH bond at alpha position, then only we will have hyperconjugation. In case of tertiary butyl group, there is no any CH bond, and therefore we do not have any hyperconjugation in this tertiary butyl group attached to the benzene ring. When you have more number of such alpha CH bonds, for example, if you are having more number of alpha CH bond, suppose in this example we have here CH3 and CH3, so there are 3 plus 3, 6 hydrogens are there at alpha with respect to this carbon carbon double bond. So here we are having more number of hyperconjugative structures. In case of this toluene, we have 3 alpha hydrogen. Here we have 3 plus 3, 6 alpha hydrogens. For example, you can write like this. In this case, we have only 3 alpha hydrogens or 3 alpha CH bonds. So here we have 3 resonating structures. Here we have 6 resonating structures. If we have structure like this, here we have 9 resonating structures. So accordingly, we have if you have more number of hyperconjugative or resonating structures, as we said, it is the modification of resonance effect. Hyperconjugation is the modification of resonance effect. So when you are having more number of hyperconjugative structures, that molecules or that bond or that compound is having more stability. So that's what about the hyperconjugation. So in this lecture we discuss about the resonance effect, some important necessary conditions required for the writing of resonating structures, and few examples we have seen to write resonance structures, and then we discuss about the hyperconjugation with the help of some examples. Thank you.